Ciao. Just don't bump it.
Good to go.
Yeah, we're good to go. You just gotta stay right in front of the screen.
Okay. So are we to go?
Yep.
Thank you.
So the golden ratio by myself and Zach Peterson. Zach is not here today. The golden ratio is represented by phi. The Greek letter looks like that. It's a very irrational number. There's actually levels of irrationality, but it's super irrational. It's equal to this. It's never ending, which is what makes it irrational. Phi is derived from the first part of the Greek sculpture Phidias. Don't know who wrote that. So you get this number using the Fibonacci sequence. It's a series of numbers you get from adding the last two numbers together, starting with 1. So we have 0, 1, 1, 2, 3, 5. So 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 2 is 5, and so on. And so what this has to do with the golden ratio is the golden ratio is 1.68 and 1.618, as we just showed on the last slide. And if you divide two of these numbers, one number by the previous number, that would give you that number. So that's the golden ratio right there. And as you go down the list to bigger numbers, it gets closer to the actual number of phi. But it does deviate from above or below the actual number, so it can be 1.618 or it can be 1.61 whatever. In the book, The Divine Proportion Studying Mathematical Beauty, talks about how when someone is driving around a corner and suddenly sees a familiar place, they get a sense of surprise gratification. The same goes for when we recognize an unexpected mathematical relationship. So consider this: a sequence of integers formed to the rule. This is basically just the rule of the Fibonacci sequence. That's how we get the number 1.618. And it also describes a sequence of numbers called the Lucas numbers that goes as such over here: 1, 2, 4, 7, 11, and 18. And so subscript 1 is equal to 1, and U subscript 2 is equal to 3. I couldn't put this in equation because slides doesn't let you, so it'd be easier to read if it was an equation. But it's basically just explaining this right here. So this number right here, these two numbers are being divided. This is from the Lucas numbers. And this is from the Fibonacci series, or this is just a random sequence of numbers, and it goes by the same rule as this. And you guessed it, these two numbers right here, the ratio is phi. So any sequence of numbers that follows this rule has the ratio of phi. And the golden section is pretty important. It's a line cut by a point. This is typically denoted as C. And this is important later on in the slideshow. Basically, this whole length divided by A is the same as A divided by B. And that also gives you the golden ratio. And then I think Zach's part is coming up. Yeah.
And this is my part of the end of the year project for Ms. Fronti. I worked with Micaiah Paramaki, and we studied the golden ratio. And my presentation today of it is going to be covering the golden rectangle, and things of that nature. So the golden rectangle is the geometric format for a lot of how we see the golden ratio or phi in everyday life. It contributes to like the spiral, and lots of art pieces, and architects use it as the formula for how they design stuff. And I'm gonna go over how you would make the golden rectangle now. So you would start with a square with all equal sides, and for these examples I used the side length A. So this is a square with all four sides equal to A. Line C is this dotted line that goes through it, and line C is made by intersecting one of the sides in the middle. So this is halfway in between each other side, and then it goes straight up to the top corner, so the opposite corner of wherever you intercepted the line. And this is line C. The rectangle is then made by saying C is the radius of a circle, and you would then draw that circle down until it's horizontal with your original A side, and this gives you the rest of the rectangle. And if we say that side A is equal to 1, then C would be equal to the square root of 5 over 2. We get that by using the Pythagorean theorem, because as you can see, this right here is a right triangle, and so we can say this side is A, or this side is A, this side is B, and that side is C. So we do A squared plus B squared equals C squared. And so this rectangle is a golden rectangle now, and it'll keep building up with every rectangle made, and you can get more and more to get the spiral, and it goes on infinitely. So as you can see, we got one big golden rectangle, and because the square is here, it then forms another golden rectangle. So this is the Pythagorean theorem, and the ratio of the ratio of the sides of this rectangle, the golden rectangle, end up being equal to 5. And so it makes sense that we would have the square root of 5 over 2 here, because we have to have an irrational number. Because as you know, phi, the golden ratio, is an irrational number. It goes on forever, like the well-known pi. And the way you can get that is by numbers like these. So we have the square root of 5 over 2, which would give us close to that irrational number, 5. What's next? Once line C is used to finish the rectangle, and you can go from there to keep making more and more golden rectangles. So once we have our main rectangle there, then we can make another square by taking this measurement here and moving it down that much. So this side is equal to this side, and that gives you another square, which puts in another rectangle. And then you can put in another square, and it gives you another rectangle, and this process can be repeated over and over again to keep getting more and more golden rectangles. The spiral you can then think about as, say, a quarter of a circle. And each circle has the radius of the square that it's inside of. So if this big square here, we say that's still length A for each side, then this circle has a radius of A. And it starts in the corner, and it goes up to the opposite corner so that the rest of the spiral can intersect each other and continue on and on forever. And this spiral is known as the golden spiral, and it's what lots of people think of when they hear the golden ratio. And you may look at that and think of a snail or a seashell, and that is true, but really there are a lot more measurements that go into that, because phi or phi is a very exact number, and it has to be that irrational number in order to be phi. And lots of people will just round it to like 1.6 or something, when really that's not it. You have to have all of the numbers. And so you may see a seashell, but the measurements might not actually equal out to a golden ratio proportion. But that's my topic of this, and there's lots more that go into it. This is used in art all the time. The Mona Lisa's been used as an example, where the spiral goes around and it comes in at her nose and it helps you focus on your face. Humans find this appealing somehow, and so they use it as much as they can. But that's what I learned.
Okay, did you want to try to do any questions, or how do we do on time?
It's about 10 minutes.
Oh, so he's got a video
I
first.
still got
No problem, go
a
ahead.
bit more. So this slide right here is basically the same thing that Zach just explained. It's just a little easier to understand. So basically, we start out with a rectangle with the same dimensions as the golden section. So remember, this is point C, cutting the line right here. So that's cut, and then we cut this again by point C right here. So that's our golden rectangle cut by C. And so now we have another golden rectangle here. And that process continues all the way down until you can finally draw that famous golden spiral. So an example in real life, a really good one would be a hurricane. The format of the golden rectangle helped produce many spirals that we see in life. For example, a hurricane. It follows the proportion of the golden rectangle, or the spiral. You can see those air boxes that are super small in there. And the spiral comes right out, looks identical to the curvature of the hurricane. Some more famous ones are the classic snail shells, the flower petals on intricate flowers, and galaxies, which are in the next slide. It's called the divine proportion because it's found in nature so often. And yeah, it's just super frequent to find this in nature. There's other things that go into it, so it's not just the divine proportion, but that is very common to find in nature. So the divine proportion is not just limited to Earth, and the coolest place in nature you can find this ratio is in outer space using these spiral galaxies. And that's shown in these pictures, the rectangles with the small rectangles are drawn right in the center of the galaxy, and the spiral just continues right out with the curvature of the galaxy. Here's another one, pretty cool. Another reason why it's called the divine proportion, you can find it everywhere in nature. That is in fact not it, Ragbo. The golden ratio was used by artists throughout history, by the ancient Greek and famous sculptor designers. The most famous of which is the Mona Lisa by Leonardo da Vinci, and the Parthenon, whose builder we already talked about a little bit, was Phidias. It's quite intriguing how Phidias used the golden rectangle to design the Parthenon. You can see that down here. The Parthenon was built so that if the length of the height is 1 unit, the length of the base is 1.68. That should ring a bell as to how Phidias designed this building. The dimensions are built to match the golden ratio. You can see that down here. Maybe wondering why the golden ratio is so widely used in art. That has to do with the strange fact that people throughout the world have always found this specific width to length ratio to be very beautiful. This has been studied and found that this ratio is a perfect ratio to transfer proportions from the plane to the brain, which means people enjoy looking at things with this property much more than things without it. For example, there are pictures displaying many different rectangles, and when asked what shape they think is the most satisfying, they typically choose the golden rectangle, which I believe is this one right here, or B.
I guess for lack of time, we can't really go too into depth in here.
So using this golden section, we can do a proof to prove that this does equal phi, and there's equations here. I want to save you guys some time, but substituting and solving, we get a quadratic equation out of this section here. And like Zach showed in his video, this is the classic 1.618 number. That's how we get that number. Another thing. Here are the exact trig equations for phi using geometry. Phi is equal to 2 cosine of pi over 5, or half secant 2 pi over 5, or half cosecant pi over 10. And the golden angle is an angle so that the angle divides a full angle GA right here.